Very good. Okay, so then we will go ahead with, in computer science and information technology, Emil Alexander-Reindorf, advised by Dr. Paul Cote, Monte Carlo Tree Search and Counterfactual Regret Minimization in Cybersecurity Threats. Emil, if you can queue up your presentation.
Can you hear me? Hello?
Yes, we can.
All right. Can you see my slides?
Yes, we can.
Okay. The title of my presentation is Lockheed Martin Fellowship Program, MCTS and CFR for Cybersecurity Defense. My name is Emil Alexander-Reindorf. Here's my outline or overview. First, I'll have introduction, and I'll do a research timeline. Then I'll go into IDS, Intrusion Detection Systems. I'll discuss Counterfactual Regret Minimization, CFR. I'll discuss Monte Carlo Search Tree, MCTS. I'll discuss my methodology and data experiments. Then I'll relate reward and regret. Then I'll discuss future works, inclusion, and references. Here's the timeline of my research. In fall of 2018, I started the Aero Army Research Office study on game theory and cybersecurity. In spring of 2019, I worked on generating MATLAB plots of utility and time. In summer of 2019, I implemented Python code for counterfactual regret minimization. And in fall of 2019, I passed the qualification exam with a paper on CFR variance. That was fall 2019, that was CFR variance. In spring of 2020, I worked with a programming language called Julia for discounted CFR. In summer of 2020, I began work on Monte Carlo Tree Search using Python. Monte Carlo Tree Search, and I was using Python. In fall of 2020, I worked on converting the MCTS Python code into MATLAB code, and I began study on decentralized partially observable Markov decision processes, DEP-DP. This previous semester, spring 2021, I submitted my research to a conference, and they accepted some of my research, and it's going to be published later this year. And during this period, this summer 2021, I'm going to work on scalable anytime planning for multiple agent MDP's Markov decision process. So I'm going to be working on this during the summer. And during this whole period, I've been reading, studying, and revising my knowledge and techniques. So what is an intrusion detection system? It's a combination of hardware and software that recognizes malicious activity within computer systems. When I say computer systems, I mean networks, PC, cloud. Cybersecurity tries to prevent the loss of data from malicious individuals. Mitigating these threats is one of the prime directives of an intrusion detection system. This research involved game theory. Now, most people have an intuitive definition of what game theory is, but if you want to be more systematic, it's when rational players try to maximize the rewards. So if you have a player who's not trying to win as much as you can, that's not rational. Or the rational player is always trying to get the highest wins or the most wins. In game theory, there is a dichotomy between perfect information and imperfect information. In perfect information, games like chess, you know all the moves for all the players. But in imperfect information, you don't know the strategies of the players, like poker. In game theory, there's a concept of regret. So regret is the realization that better decisions existed for past decisions. So I played left when I should have played right. I went up when I should have went down. I did the opposite of what I was going to do. Counterfactual regret is a kind of regret that minimizes total regret. So you see this equation regret, and you see the terms for regret, and then you see this another equation, counterfactual regret. Counterfactual regret has a greater impact on total regret, so it's a better version of regret. There are many terms in the equation, but the main thing is that the counterfactual regret minimizes the total regret more than normal procedures. Here I have a plot of counterfactual regret for rock, paper, scissors using Python. Like initially, if you look in the corner, you can see that this is rock, paper, scissors. Like rock is being played 3%, paper 0.4, and then scissors 0.18%. And you can see the utility is kind of low. But when you play rock 1/3 of the time and papers 1/3 of the time and scissors 1/3 of the time, so each is a third, you get a higher utility. You maximize your utility. So that's what counterfactual regret is teaching us. It's teaching us if we play rock 1/3 of the time, paper 1/3 of the time, and scissors 1/3 of the time, you maximize the utility for the game. Here's some Julia code for discounted counterfactual randomization. And you can see there's something called DCFR and CFR. CFR is vanilla or linear CFR, normal CFR. But you can see DCFR in blue, it converges faster with more iterations. So if you have the alpha equal to 1 and beta equal to 1 and gamma equal to 1, you don't converge as much. But if you have alpha equal to 3/2, beta equals 0, and gamma equal to 2, you converge much sharper. Now I'm going to discuss Monte Carlo tree search. In Monte Carlo tree search, there are 4 phases. You have selection, expansion, simulation, and backpropagation. For selection, you're choosing the nodes. For expansion, you're making the tree larger. For simulation, you're executing the game. And then for backpropagation, you're picking the nodes that have the highest number of wins. For the code, I converted the selection, expansion, simulation, backpropagation all into functions. After I converted the functions, I ran the code. Here's a slide on MCTS applications. MCTS can be used to solve board games, real-time video games, incomplete information games. It can also be used for war games. And MCTS can be applied to the cybersecurity scenarios modeled as games. I told you that in MCTS you have the selection stage, which you go through the nodes. But you can either go through nodes that you know, or you can explore it or go down the tree. So in this slide, you can go to with these nodes, existing nodes, or you can expand things or go through the nodes deeper.
So, Neil, you're at 9 minutes. You're at 9 minutes, okay?
Okay, 9 minutes, okay. So this term is for exploitation, and this term is for exploration. For this project, I juxtaposed the default path versus the alternative path, and there are 1,000 iterations. So I'm going to go through some of the observations that I made when I did the 1,000 iterations. Sometimes there was a bifurcation in the nodes. So you can see these 2 nodes, they're shared, but then this goes down here, and this one goes up here. So that's one pattern. Here's another pattern. There's a deflection. So you can see these 2 nodes are shared, but then there's a deflection here. There's a deflection down there. Here's another pattern. There was divergence. So these nodes go down while these nodes go up. So that's another pattern. And there's an example of convergence. So this one is coming down and this one is going up. So that's another pattern. And then there's a parallelism. So these nodes go up and these nodes also go up in the default and the alternative. And there's another example when all the nodes are the same. So the wins, the losses for the alternative, and the default and alternative are the same. So it's known that minimizing regret is maximizing reward. Detailed this research description. It is possible to minimize the counterfactual generalization by checking the backpropagation phase of the Monte Carlo tree search. So by maximizing the reward of MCTS, you minimize the regret. For future work, I want to do quantum MCTS using D-Wave and Amazon Web Services bracket, Amazon Web Services bracket. Conclusion, maximizing the reward has potential of minimizing regret. Further experiments will prove the relationship between reward and regret. Here are some of my references for this research. Thank you.
Thank you, Nia Emil.